What's up at home, people? Before this lecture that you have clicked on, the day before I introduced weak and strong acids and weak and strong bases. I'm not going to reteach the whole thing, but I do want to show the slides that were used because it might, if you pause and you read over what's there, I think you can figure it out because the skill itself is not that tough. So as I hold up slides to you, click pause if you need the data so that you can get it down and then you can kind of analyze what you're looking at. So this slide right here that you're looking at is the rules for determining a strong acid versus a weak acid and a strong base versus a weak base. And then what you'll see on the slides that I'm about to show you is examples with the answers on whether they're weak or strong. So again, if you pause the video, compare to that first slide, you should be able to easily decipher how I'm connecting whether I'm calling it strong or weak. So here was our first section of examples with the answers. Alongside our second list of practice problems. As always, come see me during tutoring or whatever, and I can work out any kinks you might have, but you can use that to figure out strong versus weak. Today, we are revisiting an old unit. As I think I mentioned when I introduced the roadmap, this topic should have been in the reactions unit. That reactions unit already had 5 lectures, so if we would have left it where it belonged, that would have been a 6th lecture, and that's just, I don't ever want your brain to explode. It would have made the test hard. So we decided to snag it out of that unit and then just cover it now. But you're going to have some old skills be brought back up, like predicting products and stuff like that. Here's something you can get out for me. Periodic table, solubility rules, and polyatomic list. Items that will help you today. Periodic table, solubility rules, polyatomic list, should have had them doing that while I was giving my intro. Okay, for you people at home, they copied this slide upon entering the room. So again, pause the video. I'll be referring back to these notes a lot. What we're going to do is look at reactions under a slightly different light. We have this thing called a complete ionic reaction, and what we're basically going to do is take some of the reactants yielding products that we did in the past, and we're going to break them down into the ions that make them up throughout the reaction. The reason this is useful is we're going to be able to see parts of the substances that participate in the reaction, and there's some parts that don't. If you look at your definitions up there, you'll see that one of our new terms is a spectator ion. Now, you know what a spectator is, right? What does the spectator do when they go to the game? Do they play the game, or do they just watch the game, right? Spectator ions that we're going to find in our reactions are substances that are there, but they're not actually a part of the reaction. So by going through this new little sequence of steps, we're going to be able to identify spectator ions and then completely remove them from our line of sight. And then we'll be able to better focus on just the substances making the reaction happen. In order for us to do that, there's 2 other reactions that we can write out of a main reaction. One is called the complete ionic, which is going to list everything that's there. And from that, we'll identify spectators, remove them, and then write the net ionic, which will only have the real players. So let's take a look at how this will happen. We'll just jump right into examples. Don't write that down. All right, for those of y'all at home, this is the example that we are doing first. All right, so what I'm going to do is translate. I'm going to go through a bunch of these revisit skills very quickly because it's not what we're focusing on today. But if I do something you don't know where it's coming from, please stop me. I'm happy to explain it. You ready? All right, old skills first. Let's translate. Potassium chloride. Potassium's K. Chloride is Cl. +1, -1, so there's no subscripts. Is combined with is the plus sign. Lead 2 nitrate. There's lead with a charge of 2 that he'll cross over to the nitrate. What type of reaction is this? Ooh, that's an old question. Double replacement, a compound reacting with the compound, and neither of them are water. Anyway, to predict the products, we swap the first part of each one. So I'm going to put the lead over here with the chlorine. It's still lead 2, so he'll cross the 2. And the potassium's going to come hang out with nitrate. Balance the reaction, of course. All right, needs to be balanced. There's 2 chlorines, so 2 chlorines. There's 2 nitrates, so 2 nitrates, and you'll see that that balances it. We also want to label solubilities. All right, now you memorized your solubility rules, right? So I didn't even need, she didn't even need to get that sheet out, I bet. But let's go through it. Stop me if you don't remember. All right. I know that alkali salts are always, that was awesome. They all said the right answer simultaneously. Yeah, they're always soluble. All right. Nitrates are always soluble. Halogens are usually soluble, but there's some exceptions. And lead is one of the exceptions. So I'm going to label him as solid. And then nitrates are always aqueous. So we have still done nothing new. Do you agree? This has all been old stuff. The new stuff is going to pop up right now. Now, before we start really analyzing this for the complete ionic and the net ionic, I want to ask, do you see any acids or bases up there compared to yesterday's lecture? Any acids or bases? No, there's not, because we know that acids start with H and bases end with OH, and that's not happening anywhere, all right? So we didn't have to think about that. It's just that's going to be a big deal in the next example, but there are no acids or bases for this problem. To write a complete ionic equation, I need to dissociate, break apart everything that will break apart. In terms of all non-acids and bases, everything that you've labeled as aqueous will dissolve in water is a way to look at it, right? All of those items are going to be pulled apart into their ion form. So let's do that. Here we go. First, I'm going to pull apart this guy, and I see 2 Ks. So I'm going to pull out 2 potassium ions. All right, remember where that plus comes from. It's nowhere tricky. It's living in group 1. The alkali metals have an oxidation state of +1. I said 2 of them because, well, for every time that this breaks apart, there's going to be 2 Ks and 2 Cls. All right, the chlorines are negative because chlorine's oxidation state is -1. Is this compound going to be pulled apart? Yes, everything that's aqueous and not acid-base is going to be yanked apart. So here we go. There's going to be 1 lead. That lead has a charge of +2. Look at the Roman numeral from the example. How many nitrates are there? You got to be careful. The very bottom, I can't make you go backwards because I'm recording. But if you look back to the previous slide, the very bottom bullet said, watch out for some subscripts becoming coefficients. All right. When this separates, there's going to be two NO3s. All right. So this is something a little different for you, but you'll get used to it. Two nitrate ions. Nitrate's charge is -1. Is this compound going to dissociate? No, solids never dissociate. All right. Hey, I want you to add another fun fact to your to the margins. I want you to also write that liquids never dissociate. You hadn't heard that fact yet. Add it to your margin of your notes somewhere. Liquids don't dissociate. Doesn't matter for this problem. I'm just giving you a well-rounded brain. Anyway, so solids and liquids don't dissociate, so I'm just going to leave him as is. PbCl2. I'm about to run out of space. The last compound is aqueous, so he's going to break apart into 2 potassium ions and 2 nitrate ions. Kind of worked. Can you see that at home? This is called a complete ionic equation, where we have represented the breakdown of every single thing in the reaction. Finally, we want to write the net ionic, which is going to get rid of the spectators. Remember those spectators that don't do anything? They're just there watching. The way that you are going to find spectators here is any substance that duplicates itself as a reactant and a product in the complete ionic equation. Look at the green. Do you see anything that is the exact same on both sides of the yield? Nitrate. Look at this. See these 2 nitrate ions? 2 nitrate ions. Now, I'm drawing a line through them. I want you to also, but don't be dramatic. I want you to still be able to see your complete ionic. All right? Because the complete ionic is the green without the crossouts. But to get to the net ionic, I need to ignore the spectators. Are there any other spectators? Yeah, the potassium. See these 2 potassiums? 2 K pluses? 2 K pluses. Yeah.
What if it's like 2
2 of them would cross out, but that is not going to happen right now. It can't happen. It's not going to happen. Now, if you are good little chemists, I meant to do this a moment ago, the states of matter should be brought down to all of the different forms of this equation. What I mean is, this should still be labeled as aqueous, just like this should still be labeled solid, and this aqueous. I mean, it's not wrong if you leave those out, it's just better chemistry if you track the states of matter all the way through your steps. Finally, to write the net ionic, you just rewrite the green equation, the complete ionic, without the spectators. So these 2 chlorines survived. The 1 lead survived. And the lead chloride. I'll go through all 3 again. This is the original reaction. This is the complete ionic. This is the net ionic. And you can find it on the first slide, I think, most of the terms. Yeah? let's do another one, but let's do it with acids and bases because it's a little different. All right, so for all of you at home people, this is the next example that we're doing. All right, let's translate together. I'm not going to draw any cards yet, but we have 4 that we're doing total today. We'll draw cards on the 3rd one. Here we go. Sodium hydroxide. Sodium hydroxide. +1, -1, no subscripts. Is mixed with phosphoric acid. Ooh, acidic nomenclature. Phosphoric ends in ic, which means originally it ended in ate if you follow your rules. Phosphate. So I need an H for the acid and phosphate. And it looks like this. Phosphate has a charge of 3 that it crosses to the hydrogen. Let's do our ion swap. We'll switch the first part of each item. So first, I'm going to send this H right here over to where sodium is, and it will be HOH. There's a better way to write HOH. Any ideas? Yeah. You can write it HOH. It's technically not wrong, but it just looks stupid. All right, so the H goes over with the hydroxide. The sodium's going to come over with the phosphate. Again, phosphate has an oxidation state of 3 that it will cross to sodium. Sodium's oxidation state is 1. Hooray! Let's balance. It looks like there's 3 sodiums. Let's make there be 3 sodiums. Now there's, what do we got? We have 3, and 3 is 6 hydrogens. So let's make there be 6 hydrogens, and I think we're balanced now. Okay, look here. This is the reason for yesterday. Acids and bases have slightly different rules for what you're going to pull apart and what you're going to leave together. All right, the opening slide already had it on there, so you know what I'm about to say if you read what you wrote. Strong acids and strong bases are going to dissociate. Weak acids and weak bases are not. So your ability to do yesterday is pretty essential here. Now, here's a fun fact though. If they are acid, you see he's a base because he ends in OH. He's an acid because he starts with H. You're there with me? All right. Acids and bases will be labeled aqueous, which is why this has the potential to confuse you. All right. If it's an acid base you're dealing with, the aqueous doesn't matter. That's not what we look at when deciding whether or not it's going to dissociate. We look at strength. So while these are automatically labeled AQ, we want to look at strong or weak. So sodium hydroxide. Well, here, let's finish this first. We'll come to that in a second. I forgot we haven't labeled these. What do you think water's state of matter is? What? No, it's not AQ. Aqueous means something's dissolved in something. What? Did you say solid? That'd be ice, but no. Come on, what do you think water's state of matter is? Liquid. All right. Which is why I gave you a fun fact on the last problem, because now you get to already know whether or not it will dissociate. Yeah, whenever you see water show up in a chemical reaction, liquid. What about the sodium phosphate? Well, I know that he's aqueous because if you use your solubility rules, he's not an acid or a base, right? He doesn't start with H. He doesn't end in OH. So we use our solubility rules, which state that all alkali salts are automatically aqueous. It's one of the Big Daddy rules, right? Okay, now let's get into the real stuff here. It's a base, so I don't care that it's aqueous. I want to know its strength. What is the strength of sodium hydroxide, strong or weak? Strong, because we learned yesterday, or you people at home learned at the very beginning of this video, that alkali hydroxides are strong, and strong samples dissociate. So let's pull him apart into 3 sodiums and 3 hydroxides. Sodium is +1, hydroxide's -1. That's why the charges exist. This is an acid. So the fact that he's aqueous doesn't matter for what I'm doing. I want to know strength. Is phosphoric acid weak or strong? Why? Oh, no, that's not the reason why. It is weak, but it's not the ivory and clay. Ivory and clay is for binaries. This one's not binary. It's weak because of the H to O ratio, right? There has to be at least 2 more oxygens than hydrogens, and there's not, making it weak. What do we do to weak acids? Keep them together. Do liquids dissociate? No, you wrote it just a little bit ago. Will he dissociate? All right, I see some of y'all getting fuzzy with me. Yes, because of the AQ. Remember, the AQ absolutely matters if it's not an acid or a base. He's salt. He doesn't start with H. He doesn't end with OH. Therefore, the aqueous will automatically split into 3 sodiums. Watch that subscript. And 1 phosphate. That's a cursive L, by the way. I found out at the very end of class that I had like 8 confused students. If I do a normal lowercase l, you think it's a 1, then you're equally confused. Hey, that's a complete ionic because it has everything. What do we need to get rid of? The stupid old spectators. All right, here we go. I'm looking. See these 3 sodiums? There's 3 here also. What other spectators do you see? None. So everything else will come down to the net ionic. And just bring down as is. Overall reaction, complete ionic, net ionic. Let's draw some cards on the next one. Right, my home people, there's example number 3. That works. Okay, let's check this out. All right, let's get some help translating to start off. Let's go to cluster 5, seat 6. Hey, Aspen. Ow. Silver, what should I write? Very good. And nitrate, what should I write? Perfect. Can you toss me, Aspen? I feel like I just tossed it to you. All right, silver nitrate is +1, -1, so there's no crisscross of charges. Reacts with magnesium bromide. Magnesium bromide is +2, -1, which is why that 2 showed up on the cross. Let's go over to cluster 2. Seat 2. Hey, 2. Am I dealing with any acids and bases in this problem? No. Nothing starts with H and nothing ends with OH. All right? Not a distinction you have to make, but I think it's handy just to have it in your mind. I'm going to do the double replacement mix up here, ion swap, which is going to give me magnesium nitrate. Magnesium crosses his 2 alongside silver bromide. +1, -1. We are unbalanced. There's 2 nitrates. Now there's 2 nitrates. 2 silvers. Now there's 2 silvers. 2-1-1 2 mole ratio. Now, since there's no acids and bases, I know that strong versus weak is not what I'm thinking about. I'm just thinking about S's and AQs. Here's a fun question. Cluster 4, seat 6, Aspen. Are any of my 4 substances insoluble? I'll give you a hint. One of them is. Which one? The very last one. Very good. It is the very last one. Because I know that my solubility rules state that bromide is usually soluble, but silver is an exception. So this is solid. Nitrates are always soluble. Bromides are usually soluble. Magnesium's not an exception. Nitrates are always soluble. And that's all I need to know. There's no acids and bases, so the AQs split and the solids don't. Wait, what's funny? You keep doing that. No, I want in on the joke. No? Oh. Let's go to cluster 2 again and talk to seat 1. Hey, 2-1. What's the very first thing I should write when I start dissociating? Perfect. Yeah, 2 AGs along with its charge, right, which is positive. All right, because it's aqueous, I know that I'm going to be separating it. There's also 2 nitrates. Is this compound going to dissociate? Yes, because it's a non-acid base aqueous. Or salt would be the other way to say it. So there's 1 magnesium ion there with his +2 charge and 2 bromide ions. Make sure you stop me if you don't know something. You're being very quiet. Aqueous, not acid base, automatically dissociates. 1 magnesium ion, 2 nitrate ions. All right, so just watch those subscripts sometimes turning into coefficients to count the ions when they split. What will that last substance do? Nothing. Stay together. We have now written the complete ionic equation. 6. Seat 5. Hey, Aspen, can you find any spectators? 2 NO3s. Yeah, there's one. 2 nitrates there. Missing his chart. And 2 nitrates there. All right, you can pass the bird. Are there any other spectators? What? Yeah, there's 1 magnesium ion and 1 magnesium ion, and boom, we are now prepared to write our net ionic by getting rid of those spectators. Bring them on down. Is this easy? For those of y'all that are not struggling with this, I have some cool news. We do have one more problem to do, so don't put yourself away. But this is a major AP skill. Like, this is majorly tested on the AP exam. So hopefully you're signed up for it. Anyways, let's see if you really think it's easy or not. I'm going to start the translation for you on this last one and then let you finish it up. For you people at home, this is our independent problem. If you can jump out ahead of me, then jump out ahead of me. But I want to know the net ionic equation. Hydrochloric acid is HCl. Potassium hydroxide is KOH. It's an acid reacting with the base, so be aware of that. When I switch these, we'll have KCl alongside HOH, but don't write that. If you get stuck, call me over. Ms. Morrison requested a shut
So that 3 doesn't ever move. But PR2, it only has that 2 because magnetization lost it over time. So when this breaks apart, there's going to be 1 magnesium and 2 bromines. When this breaks apart, there's nitrate is always in O3. This is part of his identity. So there's not 3 of anything. I mean, there is, but not in terms of counting. So there's 2 AGs and 2 O3, 2 of those items. It takes practice. I know it's challenging. It just takes practice, and you'll start to just automatically see it.
As we near the bell, I'm going to push forward. So here we go. It's acids and bases, so it's like that second problem we did. It's already balanced 1 to 1 to 1 to 1, so that was nice. I know that acids and bases are automatically labeled aqueous, but it doesn't matter because we don't look at that. I know that alkali salts, that guy I'm pointing to is not an acid or a base. He's different. Doesn't start with H or end with OH. But my solubility rules say that alkali salts are always aqueous. And then what did you label water? Liquid, yeah. All right, very good, very good. So here we go. Aqueous acid, I just care about the strength. What is the strength of HCl? Strong. I bring clay, right? Back to the Plato party. Strong acids dissociate. All right? Aqueous base, I don't care that it's aqueous. Is that a strong or weak base? Strong. Alkali hydroxides are strong. Whoa. So he dissociates. Aqueous salt. Now I care about the aqueous, right? If that's labeled AQ and it's not an acid base, automatically dissociates. And liquids never dissociate. Spectator ions, we've got the complete ionic written, but I see chlorine ion and chlorine ion, I see potassium ion and potassium ion. The net ionic will be written without those spectators. I'm so proud of y'all. They did so good today.